When we talk about moving fast, what do we mean? Well, we're saying that we cover a lot of distance very quickly. So a lot of delta D, change in distance, over change in time, a relatively small change in time. Okay. Hey, if we keep on driving a race car around a racetrack many times, do we actually get anywhere? No. So our change in position, or change in displacement, which is sometimes used interchangeably, well, what's that? That's nothing. And therefore our average velocity is going to be, notations may vary slightly on what average abbreviates to. Our average velocity is going to be nothing in that case. Now why do I, and many other physicists, occasionally use position and displacement somewhat interchangeably? Okay guys, stand 5 meters in front of me. Wait a second. That's a position, but it specifies a start point, which is me. So 0 meters in front of me. So the difference between the two is 5 meters in front of me minus 0 meters in front of me equals 5 meters to my front. Hey, that's a displacement. So a position also gives a displacement from the reference point. That's why we often use change in position and change in displacement somewhat interchangeably. Now a position time graph describes the motion of an object with position on the vertical axis and time on the horizontal axis. Like this. Now, the slope is a measure of the steepness of a line. As we can see, lines can have different steepnesses. Now, when it comes to change in position over time, what does that mean? Well, here the position is increasing very quickly over time. Here the position is increasing slower. So we're going in the positive direction pretty fast, and then we slow down, and then we go in the negative direction. Or we go a negative speed in the positive direction. And, well, here we see that we started a little bit short of the 0 line. Usually the axis used is a 0 line, but it could just be some reference number. So we start a little bit short of that, which means that if this is, say, a biker, we started a little bit behind our reference point. And then we biked, say, forward or to the whatever direction is positive. Very quickly, we slowed down, or rather, we suddenly changed speeds, which is, of course, very unrealistic. And then we suddenly changed speeds to bike back to our beginning point very quickly. Now something is wrong with this formula here compared to this graph. So how can we fix this? Hey, slope is change in distance. No, it should be change in position. This is a vector. Being a vector is very important because it allows us to decrease it. If it was a distance time graph from which we can calculate average speed or instantaneous speed, i.e. the slope for that particular piece of the graph, well, if it was distance time, then, well, we can stand still. So distance does not increase. It's a flat line. The rise in the line is 0, and the run is however long we stand still. But if we move in any direction, then what happens? Well, our distance changed. We moved with some speed. We increased the distance covered, which means that the distance would go up. Distance time graphs should not slope downward unless they're supposed to actually be position time graphs, because the distance you cover can only increase or stay the same. Now what happens when we divide a vector by a scalar? Well, we end up with another vector because going 1 kilometer in some direction, if you do that twice, that's 2 times that same change, and that's 2 kilometers in that direction. Still a vector. So the average velocity of a moving object is the total displacement traveled divided by the total time elapsed. Total displacement means you add all the separate displacements, because you might have several steps to a journey, together and then divide. Now motions could have uniform velocity or non-uniform velocity. So, what are these? Well, uniform velocity is constant speed in a straight line. Now the speed can be 0, which means that the position time graph is going to be a flat line. The position is the same with respect to some reference over time. It doesn't move. Now, what if the position does change? Well, it could be uniform, so same speed, same direction, or it could be non-uniform, like this. Now, it could be the same speed, but is the direction the same? If I let go of the marker, will it always fly off in the same direction? No. So, non-uniform velocity is changing speed or change in direction, or both. So if we see a straight line on a position time graph, then we know that it's a uniform velocity. Now, what makes the velocity change? Velocity is what makes position change. Speed is what makes distance change. They are closely related, but not quite the same. So for velocity, what makes it change? Well, we call that acceleration. And non-uniform velocity is a property of accelerated motion. So we can determine types of motion from position time graphs, such as these. So to describe the motions depicted, this graph has the object at some position that is to the east of the reference point, and it stays at the same position. So stationary and east of reference. Now what about this one? Well, that's positive. This is negative, generally. Sometimes you do see the axis being not 0. Okay, so this is stationary because we can see that the slope is 0. It's a flat line. The position does not change over time. So stationary, west of reference point. Now what happens if the slope is not 0? Well, in this case, we begin at the reference point and we are moving to the east because our position eastward is increasing. At reference, constant. Now yes, okay, you can say constant speed east because, hey, you specify a direction. So speed east is fine. What about this one? Well, we didn't start at the reference point. So, start east of reference. And, well, it's a constant velocity because it's a straight line. And which direction? Well, the slope is positive. The positive direction is east. Therefore, this is going east. To say that it has a constant speed, well, the speed is a magnitude of the slope here. Because, hey guys, we're going 100 kilometers per hour west, but the positive direction is east. Oh, that means we're going a negative 100 kilometers. The speed is still 100 kilometers. Absolute value is distance from 0 on a number line, which means just taking off the negative symbols. Constant speed east. Now you could say eastward, because in this case we start east of the reference point and have a constant speed west or westward. Grammar and conventions may vary slightly. Start east of reference. Constant velocity, or you could say going west, but we'll just stick to west for time reasons. Now here we have point A to point B by 8 kilometers north, 8 kilometers east, and 8 kilometers south. And this is in 8 hours. 8 hours of walking. Kind of tedious, I guess. What was our average speed and what was the average velocity? Well, speed is you add all the distances up together. So V average is equal to delta D, no arrow, it's not a vector, divided by delta T, which is going to be, well, our total distance was 8 plus 8 plus 8, and this is divided by 8 hours. This is going to be equal to 24 divided by 8, which is 3 kilometers per hour. Now what about velocity? Well, for average velocity, we have displacement over time, which is, well, we went 8 kilometers north, 8 kilometers east, and 8 kilometers south. So this, we can draw this by vector scale diagram method, which means connecting the beginning of the first vector to the end of the last one. Or we can do this by math. 8 kilometers south is negative 8 kilometers north. So when we add them together, we get 8 kilometers east. So 8 kilometers east. Yes, technically we should probably also add the other ones. Plus 8 kilometers south. But hey, we're just going to cross them out because they cancel. And this is divided by the time, which is 8 hours. Please note that the units are not necessarily required. In fact, they're usually not put in when you're just substituting like this. And in fact, you generally separate your two dimensions into separate velocities, and then you add them together. Well, okay, you separate them into separate displacements, and then you find the total displacement, and then you divide by time to have a velocity that matches the direction of the displacement. But it can also be done the other way around. Like many things in math, and physics is considered by many mathematicians to be applied math. Okay, so this is 8 kilometers divided by 8 hours, which is 1 kilometer per hour east. The square brackets are used for directions in the same sense that you may have used them before for transformations, namely translation, when you were first learning Cartesian grid. Like, say, move something 3 grids to the right and 5 grids up would be square bracket 3, 5, other square bracket. Now, in summary, average speed is equal to the total distance traveled divided by the time it takes. The position time graph describes motion graphically. The slope of the position time graph, which is the rise, so whether it goes up or down, that's still called rise. Down is negative though. It's divided by the run, the horizontal distance, or rather horizontal dimension, because that's usually time in physics. So the slope of the position time graph gives the velocity of an object. Well, it's usually time on the x-axis for now in physics. Later on we'll have many other things. So average velocity is equal to the total displacement divided by the time it takes. In other words, velocity describes the change in position over time, not change in distance covered, which speed does. And motions with uniform or constant velocity are at a constant speed in a straight line. If it's accelerating, then it won't have a constant speed and constant direction. And accelerated motion is non-uniform motion. If you have an object with constant velocity, it has a position time graph, that is, a straight line. Because, well, the change in position for every unit in time is the exact same. So the slope is the same, whether it be positive, 0, or negative. Distance time graphs cannot have negative slopes. Kind of like if you're pedaling on an exercise bike, it's not going to say that, oh, you are pedaling backwards, and therefore the distance you cover is negative. No, you're still covering distance no matter how you pedal. Of course, that's the exercise bike's computer telling you that you're covering distance, although your legs are, in fact, covering distance. Well, that's it for this section, and see you next section when we start talking about acceleration.